So we have one more big result to talk about, and that's called Morera's theorem. Okay, and again, I'm going slightly different order than the book, but all the same topics. And so Morera's theorem tells us the following. So let me just jump right in and tell you. So let G be a region. So let G be a region. So an open connected set. And suppose that the integral of f over gamma is equal to 0, and that this is true for all closed paths gamma. Okay, so if this is true for all closed paths gamma, then it turns out that that implies that f is holomorphic. So then f is holomorphic, and f has an antiderivative, capital F. Okay, so f is equal to capital F prime. I want to write that just a little better. So little f is holomorphic, and little f is the derivative of some function capital F for some holomorphic function capital F. And here this is holomorphic on G. Okay, I probably should have worded that a little differently, but there we go. So let G be a region. Suppose that the integral of a function is 0 for all closed paths gamma. That implies that f is holomorphic on G, and that little f has an antiderivative, and the antiderivative is also holomorphic on G. Okay, so this is called Morera's theorem. This really is just a combination of all the stuff that we know so far. Okay, so the proof is really straightforward. Okay, so the proof. First, we know that there's an antiderivative because of the what I like to call the analog of the fundamental theorem of calculus, right? So the existence of an antiderivative. So the existence of an antiderivative follows from how we defined the antiderivative. So if you remember, there was a result where we defined a function capital F that was the integral of little f over gamma sub z, where what we do is you start at a fixed point and then you think about some path that varies, and so the path is going to go from some z naught to z. And as you change z around, as this value of z moves around, so if z is over here, then you get a different path. So gamma of z is just some path from some fixed point z naught to some other point z, and it doesn't have to be a straight line, just any path between those. And it turned out that that is what gave us the antiderivative. Okay, so this is something that we already know. We know how to find an antiderivative using an integral. And then once you have an antiderivative, everything else falls perfectly into place, because if capital F is holomorphic, and of course capital F is holomorphic because capital F has a derivative, namely little f. So notice that if capital F prime of z equals little f, which is what an antiderivative is, that implies that capital F is holomorphic on G, since this is true for all values z and G. And if capital F is holomorphic on G, then capital F is infinitely differentiable, and therefore little f is infinitely differentiable because this is one of its derivatives, and then you can differentiate this infinitely many times. So that implies that capital F is, let me just write this a little better. So capital F is holomorphic, so capital F is infinitely differentiable on G. And therefore, little f is infinitely differentiable. So it's holomorphic and infinitely differentiable on G. I really, now we know that that's redundant. I don't need to say holomorphic and infinitely differentiable. I can just say holomorphic. Okay, and that's basically the proof. Okay, so there we go. So that's Morera's theorem. So this says again that if you have a function little f and the integral is 0 for all closed paths gamma, then that function little f is holomorphic and has an antiderivative. Okay, so that's Morera's theorem.